That's wonderful, because I think it's 9:01 in my computer, so let's get started. So it is good morning, everyone, or good afternoon or good evening. It's my great pleasure to introduce today in the Topos Colloquium, Professor Glynn Winskel, who, as you can see, is now with Huawei. If I hope I'm kind of not mispronouncing it totally, but you know,
me
it's a
anyhow.
hard one. Yeah. But and also it's Strathclyde University. Glynn and I go together a long time, and I'm not going to tell you all about the longs. Glynn is a very important professor of theoretical computer science. You know, I think it's the only professor I know that has been a professor in 2 different stints in Cambridge Computer Laboratory. He started doing maths in Cambridge a while back, and then he did a master's in, he did a BA in maths, then a master's in Oxford, and a PhD in Edinburgh, when he started kind of being the important person that he is in terms of concurrency. And so he will be talking to us about making concurrency functional, which is a extraordinarily interesting topic, at least to me, but I hope everyone else will enjoy it too. Take it away, Glynn.
Thank you very much, Valeria. And it's a pleasure to kind of see you again, and also to be talking about stuff that really we were doing back in the 80s with Martin. At least it's the work here connects with that. Both the work that you were doing on dialectica categories, but also the work on generalizing Girard's ways of handling polymorphism and so on with dependent types. Okay, so making concurrency functional, and this is really about combining 2 of the major paradigms of computation. The functional one, which is historically very important in our subject. It's really, I suppose, a cornerstone through the Church-Turing thesis, thinking of computation as functions. And then, of course, interaction is largely then by function composition. And then less settled, I suppose, is this other paradigm of computation, computation as interaction, in which you're not so much interested perhaps in the input-output behavior of something, but how it interacts with its environment and interacts with other processes in the environment. Here I'm going to be using many of the approaches are often syntax-driven. Here I'll be using, in contrast to that, a rather maths-driven foundation, which is really trying to be a new semantic foundation for computation, which takes account of interaction. And it's based on distributed or concurrent games built around event structures, with interaction given by composition of strategies. And it's a kind of generalized domain theory, or that's the hope that it becomes something like that, in which types or constraints are represented by games, and programs and processes are represented by strategies. And it gives rise, like many mathematical structures, gives rise to its own syntax. So this is about building bridges between the functional and interactive views of computation, and in particular, observing that out of these concurrent games and strategies, by looking at particular games, one obtains as subcategories many of the refinements people have put on functions in order to cope with interaction of various kinds. So the kinds of refinements I'm thinking of are here: lenses, optics, combs, containers, etc., etc. How they arise, or partially arise, in terms of these concurrent games. So let's start with oh dear, I'm not able to advance my slide now, don't know why. What should I do? My slide is somehow frozen.
I don't really know, but I expect
it was working.
You're saying kind of come out and come back in or something.
Yeah, I'll try that.
Tim, do you have any suggestions for us?
You could try. No, actually, I don't have anything.
Don't know why it's. Oh, wait a minute. Now it started working again. God knows what that's about. So So this is, okay, so let's start with a simple recalling how functions are used and how they can be modified to cope with interaction. Of course, a function looks like this from input A to output B. And then, of course, we generally compose them in this way, but we might want to think of a function as interacting with its environment, in which case we're concerned with parameterized functions, which take maybe some input from the environment. But if they can take input from the environment, why can't they also give output to the environment in a slightly more extended parameterized function like this? And then we can start composing such processes regarded as interacting functions. But the interaction doesn't need to just go one way, it could go both ways. So we can get a picture looking rather like this for the kind of way in which processes represented by functions might interact with each other. So we have functions of this kind, and if we add in, as David knows all about, backpropagation to cope with learning and so on, then we end up with functions with inputs and outputs of this rather complicated form. Of course, this is glossing over a lot. It's glossing over the nature of functions. Generally, we need enrichments to cope with computation phenomena, which is often maybe partial because of divergence, in which case we might want partial functions. And then the pictures came by rather quickly, but of course you could detect loops there as well. So if you could cope with loops, perhaps you want to have continuous functions. But then here's a warning, because we might want our functions to be non-deterministic. And as has been known since the Brock-Ackermann anomaly of 1981, it's hard to give input output some compositional semantics for non-deterministic functions like this, of the kind that could be coped with here. Then, of course, there are other extensions you might want to go into in the probabilistic, quantum, and smooth, and so on. Okay, but another point is that functions perhaps are a little static in the way that they describe the dynamics of interaction. Through dependent types, you can help this to some extent by making functions depend on the previous occurrence of certain input and so on. But I think that we would like, in general, a way to describe and orchestrate the temporal pattern of interaction, the fact that the linkage that you're seeing a bit of here could change dynamically, and moreover have a better capture better the fine-grained dependencies there might be between these various linkages and functions. And so that brings me on to the model that will be the fundamental model of this talk. It's form of event structure, and for the talk I've chosen the simplest one I can get away with just a binary conflict, and that will be sufficient. So what is an event structure? It's really consists of a set of events or event occurrences with a causal dependency relation. So when you see something like this, E prime below E, what that means is in order for E to occur, E prime has got to occur previously. And then there's a binary irreflexive symmetric conflict relation, which says when one event excludes another one. And we'll have a couple of axioms. The first one will say that an event only depends on finitely many events. And moreover, that conflict is inherited upwards with respect to causal dependency. Now, in this model, you can see when events are causally independent or concurrent, namely when they're neither in conflict nor causally related. So here's a little picture. I've drawn the immediate causal dependencies as arrows. I've drawn the conflict as a wiggly line here. So this is an event here on the top left, which depends on two events, the ones I'm indicating. I hope the cursor is visible. It depends on the event on which it depends here in the middle is in conflict with the one on the right. So if the event on the right occurred, it would exclude the occurrence of this event. It's in conflict with it, and therefore block the occurrence of this event, which causally depends on the event that's being excluded. So So once we've got event structures like this, they're accompanied by a notion of state called the configuration. A configuration is the set of events that have occurred up to some stage in the computation. So it's a subset of events which should be consistent. It shouldn't have any conflicting events in it. And moreover, it should be such that, and you know that when an event has occurred, all its causal predecessors have got to have occurred as well. So it should be downwards closed with respect to causal dependency. So one has event structures together with this notion of configuration. They subsume trees. So with an eye to the future, here's a tree that you might think of as representing a game tree, representing two possible moves at the beginning that then can be followed by subsequent moves. The two moves initial moves are in conflict with each other and so on. But one advantage of event structures is if we imagine we had one game and we put it in parallel with another game, we could just represent the combined game trees, not by shuffling them together in any way to get a tree, because we don't need to. We can just lay them side by side, and that would still be an event structure. And so one could, in that case, imagine this is a game, green game, and there's a red game, and you could imagine a situation where if a player wins in the green game and another player wins, say, in the red game, then they can start a new game and then resume in that kind of way. And this is something that you can do directly with event structures, which would be hard with trees. Now we're going to take this model and make it into a model of games. And the point is that games represent give a good way of representing interaction. And I learned about these ideas, I guess, first of all, from Conway as a student, though I didn't quite recognize at the time the significance of what I was hearing. So this is the idea that really games for interaction underlies the work of Conway, and as probably most of you know, that got tidied up and made more categorical by André Joël, apart from a little mistake he made in the parallel composition called sum there. Anyhow, but so this is an idea of using games as a model for interaction. Specifically, we're thinking of two-party games, and we're giving a reading of player and opponent as process, player representing the process over which we have control, versus the opponent, which is the environment over which we have no control. And generally, if you have such two-party games, then you can do a dual operation of just interchanging the role of player and opponent. This is technically useful because we often think of a strategy as being a strategy for player. So we can talk about a counter strategy or a strategy for opponent as being a strategy for player in the dual game. Often in this kind of situation, one has a parallel composition of games. You can, if they were represented by event structures, you could lay them side by side, or you could physically just lay the two games of chess side by side and so on. And the idea that was underlying Conway's books on surreal numbers, on numbers and games, was that you could you could compose strategies in this kind of way. You could talk about a strategy implicitly for player from a game G to a game H as a strategy in the compound game got by taking the dual game of G in parallel with H. And if you had another strategy going from H to K, namely something in this compound game here, dual game of H in parallel with K, then informally, you could make those strategies, you can compose them against each other by making them, compose them with each other by making them play against each other in the common game H, where one was making a move of player, the other would see that as a move of opponent, and vice versa. So this is a general scheme for building a category, and what you find is often, most often, that there's an identity. The identity of that strategy is given by a form of copycat strategy in which player copies the moves of opponent. So here's a particular concrete way of thinking of that. We imagine we think of the game of chess as the one in which player plays black. That's this thing, copy of chess on the right. And then if we want to, the copycat strategy will go from the game of chess to the game of chess. So it will be a strategy in the compound game got by taking the dual game of chess in which player plays white in parallel with this original game where he plays black. And the copycat strategy would be such that player copies whatever player copies whatever opponent does. So opponent, he waits for opponent making a white move, then makes the white move. That's over on the right-hand side game, then makes the white move, the corresponding white move in the left-hand side game, and then waits for the black move and so on, and then copies it over. So basically has dependencies on moves from left to right and right to left, which give the copycat strategy. So the idea is to take this Conway-Joao method of constructing a category and start out by replacing the usual game trees by event structures. But event structures in which the events represent moves of player or opponent. So the events are accompanied by a polarity plus or minus to indicate whether they're moves of player or opponent. And because we'll want to have that copycat is a deterministic strategy, it's convenient to assume throughout this talk, at least, that all the game is race-free in the sense that there's no immediate conflict between player and opponent events. Player and opponent events can be in conflict, but that's only because it's inherited from earlier conflict between purely player events or purely opponent events. Okay, but there's no immediate conflict there's no races between player and opponent for playing that particular move. Okay, well, we've seen event structures, and now I've just asked you to imagine these events tagged by player or opponent, plus or minus. And then there's an obvious dual operation, which is just to reverse the plus and minus. In that way, you switch the role of player and opponent. And we've seen, as in trees, that we can take the simple parallel composition of two event structures just by taking the non-conflicting juxtaposition of event structures. And then provided we have the notion of a strategy in a game, we can know what a strategy from a game A to a game B is. It's namely a strategy in this compound game here. But of course, this begs the question, what is a strategy in a game? Well, roughly, a strategy should be which is a strategy for player, should be a choice of moves for player together with how they, will then depend on which will causally depend on moves of opponent. So let's look at copycat. We want to have a copycat strategy going from A to A. Here's the original game A looking something like this. This might be part of what I've drawn may be part of a bigger picture. There may be more conflict, there may be more complicated causal dependencies and so on. And then the dual game will look the same, but for a reversal of polarities. And then when we produce the copycat strategy by, in the spirit of copycat, making the player moves causally depend on the corresponding opponent moves in this manner here. And that gives us the copycat strategy. It requires a little bit of checking that you don't introduce any causal loops by doing this, that you do indeed get an event structure. Once you tidy up and make sure that conflict is inherited upwards with respect to this enlarged causal dependency. But not all strategies are quite as simple as that. They can't all be got just by adding extra causal dependencies to the game. So we will take a strategy to be a map from an event structure S, which is making the choices of moves that player wants to make. And so we'll regard a strategy as a map going from an event structure S into the game. And it's going to be a map of event structures. This is something that's existed before. It will be such that satisfying something, it will satisfy some extra conditions as well to make it a strategy, but it will be such that to being a map of event structures will mean that if we have a configuration of S, its direct image under the function should be a configuration of A. And moreover, we want a local injectivity condition that says if you have two moves that are made in a configuration S, and they go to a common move in the game, then they'd better be the same move. And what this is basically saying is you can't make more moves in the play than the game allows you to make. So here's an example of a strategy presented as a map. It's the game is one in which which just consists of 3 concurrent events, 2 opponent moves and 1 player move. And you can think of the configurations. They're just going to be all the subsets of of this trio of events here. Think of the configurations as positions of the game. And then we might want a strategy which is to answer any move of opponent by a move of player. And we could realize that by this event structure here. If opponent makes a move either on the right or the left, then we make a move. Then we make a move of we make the only player move that we've got here. But we have to make sure that those 2 events are in conflict. Otherwise, we would break this local injectivity. Okay. So we can think of the configurations of S as being states of play, and we can think of the configurations which they image to under sigma as being corresponding positions of the game. But that's not all we'll need for a strategy. It should be receptive and innocent, in the sense in that we don't want player to be able to unduly influence the moves that that opponent can make beyond the constraints of the game. So informally, somewhat informally, an opponent move at a position in A is allowed at the state if you're in a state of play and you look at the corresponding position, and if the game says a component can move, then you better allow that also in the state of play. And moreover, you don't want to be able to inhibit what the opponent can do. So the only there can be extra causal dependencies in S that don't exist in A, but the only additional immediate causal dependencies which can't be reduced to smaller causal dependencies between are of the form a player move causally depends on opponent moves. Okay. Now I'll say more about where these conditions come from in a moment. But but when games, normally people think about games being trees, and then often strategies are expressed somewhat informally. We can't be quite so informal with event structures, but the notions we develop with event structures reduce to what you're used to. So for example, this is a game tree here. Opponent makes a move, then player can make this move or this move, and so on. If we wanted to say at this point here where opponent has made this move, we make the move to the right, and then we make the move to the left. We could do that. We could do that by just having this particular map specifying the choices that we're making. This is a kind of strategy in which player decides to take the initiative and go off and do his own thing here. But what about composing strategies? How do we do that? So if we have 2 strategies, sigma and tau, one going from A to B and one going from B to C, what we'd like to do, at least informally, is play those strategies against each other over the common game B. And we can do that by synchronizing the complementary moves that we see associated with sigma and tau over the common game B. And we can do it via pullback. So the idea is, from a if computer scientists will know about synchronizing processes, and this is an example of a synchronizing processes S and T synchronizing over that common interface B, but mathematically we can achieve that by using pullback. And what the end result will be, this is to give you some idea of the technology that's underlying this. The result will the way that we get a configuration of the interaction of these two strategies without hiding anything for the moment. We need to eventually hide the moves over B. The way we get that is by taking a configuration associated with sigma and a configuration X associated with sigma and a configuration Y associated with tau, and gluing them over their common part, provided no causal loops ensue in that operation. So configuration X of S images to a position which is a position in A and a position in B. Configuration Y in T images over to a position in B and a position in C. To be able to glue them together, we insist that the positions in B are the same, that XB equals YB. And then we join them together, provided by just gluing them together at that common part got by gluing them together over XB, and which equals YB, and provided we don't, in doing that, introduce any extra causal loops. So that's how we do some of the technology we use in order to do this synchronization operation. But of course, when we do this synchronization operation, we've got these synchronization events where opponent events of sigma have been instantiated by player events of tau and vice versa. So we end up, by doing this pullback, with a, if you like, where we're playing over this common, but we can still see the plays that are going on over this common subgame B of the two strategies. And we'd like to hide that. Oops. So here we're using a bit more technology, but I'm going through a bit too quickly, I suppose, which is that we've got this where we've taken the composition of two strategies without hiding. We can compose that with a map where we just elide B, its identity on everything other than B, and it's undefined there. That composite gives us a partial map. We can look at the domain of definition of that and restrict that original map to that domain of definition. And that gives us the definition of composition of strategies, which includes hiding of that intermediate game B. So that's how composition is defined. It's giving you a kind, it's very quick, I suppose, it's probably too quick, but it's giving you an idea of some of the technology you need in order to define composition of strategies. Well, it turns out the conditions of receptivity and innocence that I sketched earlier are precisely those needed to make copycat identity with respect to composition. So it provided a rationale for Sylvain Rideau and myself for the definition being correct. I'll just briefly indicate a little bit more formally what it means to be a strategy in terms of lifting conditions. If you have a state of play X in the strategy and it goes to a position sigma X in the game, and the position in the game can be, from that, opponent can make some moves and go to a new position Y, then receptivity says that in the state of play X can be extended uniquely to another state of play X prime, which images down to that new position. And the extra condition, the other condition of its so-called innocence, says that if you're in a state of play X, which images to a position sigma X in the game, and you could, at least in principle, retract that via pure purely by player moves, and that's what this plus is meaning here, to a position Y, then that retraction can also be done within the to the state of play. And another way of saying that, which is perhaps going to be more relevant in the future, is that the strategy can adjoin causal dependencies, but the only extra causal dependencies it can adjoin are ones of the form: a player event depends on an opponent event. Other causal dependencies will block the retraction upstairs here. So that's an indication of a more formal way, and there's a story that then takes off from here to Scott order and connections with profunctors and so on, because of course we're getting very close to discrete vibrations here and to pre-sheaves and etc. Anyhow, we've got defining strategies in this way gives us a compact closed bicategory of distributed games and strategies. We can look at that. We'll look at winning conditions and imperfect information in a moment, but already we can say some interesting things. The first thing I should say is that if we look at tree-like games, we recover the usual notions, with one little caveat. In these games, no one is forced to play. They can just decide to not move forward. That's possible. Okay. If we want strategies to move forward, we have to encourage that moving forward, that progress, by using winning conditions of the appropriate form. But if we look beyond trees, and we can because we're basing our games on event structures, there are some surprises. This is an old surprise, but it still was a surprise, that one starts recovering by restricting the games in certain ways. One starts recovering well-known structures that have been around for a number of years. The first thing we notice, well, first of all, I should say what I mean by a deterministic strategy, because some of the cases will depend on working with deterministic strategies. A strategy is going to be deterministic when conflicting behavior of player is inherited from conflicting behavior of opponent. So player doesn't introduce any conflict themselves. So in the S part of a strategy, if you see conflict between player moves, then you can trace back to causal dependency and find it being due to conflicting behavior of opponent. All right, first thing, let's look at some very stupid games. So games A and B, which consist purely of player moves. So all the moves are player. Opponent doesn't even get a look in. Now think about what a strategy is from between two such games, going from A to B. It's going to be a strategy in a compound game like this. And so if you think about it, B, of course, is just going to be purely positive moves, or player moves, I should say, whereas the moves of A perp, the dual game, are going to be just purely opponent moves. Now think about the conditions on a strategy. It should be receptive. So whatever opponent is allowed to do in the game, that should be possible. That should be possible in S. Any player move has got to be a move in B. And the only causal dependencies we're allowed to introduce in the strategy are ones going from opponent move to player moves of this kind here. So what we're getting is a situation where we have moves in B which are triggered by certain opponent moves. Find some finite set, say, of opponent moves in the by some finite set of opponent moves. And if we understand this to be a deterministic strategy, then given some configuration of opponent moves, then we can only expect to get a configuration of player moves as output, because we're not allowed to introduce, through player moves, we're not allowed to introduce any conflict. So what this means is that if we look at deterministic strategies between these stupid, purely player games, we end up with certain kinds of functions between their configurations. And in fact, if you look, you can characterize the configurations of such event structures. Well, strictly speaking, if I enlarge the conflict to not be binary, they'll be exactly the DI domains that were used by Gerard Berry in his domain theory based on stable functions. And the deterministic strategies correspond exactly to Berry's stable functions. And this is a Cartesian closed category of domains. It's a kind of French domain theory. It's called stable domain theory, which came into greater prominence in the mid-80s. Berry did this in 78, came to make greater prominence in the mid-80s due to its kind of rediscovery by Jean-Yves Girard in his coherent spaces. His coherent spaces can be viewed as a very special kind of event structure in which the causal dependency is trivial, just identity. And his state and the functions that he was working with were these stable functions that then got refined to being linear stable functions and so on. So anyhow, so we rediscover stable domain theory as a subcategory of deterministic strategies between these stupid, purely player games. What happens if we don't restrict to deterministic strategies? We end up with something that's not so well known, but has been important in solving that anomaly discovered by Brock and Ackerman. We rediscover a model that underlies compositional semantics of non-deterministic data flow. If we look at in such a strategy, the purely player moves, then we see, just as before, that a purely player move will give rise to an output in B and be associated with making a certain demand on input in A. So we've got something that's in the literature is called a stable span, but you can think of them intuitively as a kind of non-deterministic stable function. And they can be regarded as special profunctors as well. They form a monoidal closed category. Parallel composition is no longer product as it was in it was product in the earlier case with stable functions. But now we have a monoidal closed category, and the trace that we get of strategies turns out to be the tricky feedback operation of non-deterministic data flow. So this time, again with stupid games, but now looking at non-deterministic strategies, we see that there's an equivalence between strategies between purely player games and stable spans between event structures. Let's up the game a little bit. We'll have games which are a little more complicated. Let's imagine that games are presented as just as parallel compositions of a purely player game, A1, in parallel with a purely opponent game, A2. And let's think about strategies between two such games, one being A of this form, A1 in parallel with A2, and another being B, B1 in parallel with B2. And imagine we want to think about strategies from A to B. With the switching of polarities that takes place, we have positive events, positive moves or moves of player in B1, just as we started out with, but also in A2 perp on the left-hand side. And then if you think about what causal dependencies there can be, they can only be from A1 perp events or B2 perp events to such positive player moves. And in fact, in this case, a deterministic strategy will correspond to a pair of stable functions where you have one function taking input here and giving output here, and another function taking input here and giving output there. So that can be summarized by thinking of a strategy as a pair of functions like this. And the composition will be given in a kind of, well, I've done it rather schematically here, diagrammatically, but the composition is a little bit complicated because you can see, as you can see here in the middle, when you compose things, you get a loop. So what we do here, so if we're going to solve that, we need to use fixed points in order to know what values to assign on this, to trace in what values to assign to trace out this middle part here. And what we recover is a model of geometry of interaction that isn't the same. It's kind of a simplification of the original model of Girard to a domain theoretic setting. So we recover Abramsky and Jagodishin's geometry of interaction construction, but now starting from stable domain theory. And this has been important, still important for optimal reductions in the lambda calculus and so on, and also in understanding token machines. And roughly, you can think of these types, the A1 and the A2, as being associated with passages of tokens both into and out of a link in these machines, in these token machines. To look at other special cases, I'm going to extend these games with winning conditions. I have to do it rather quickly, but and also with imperfect information. So a winning condition in a game it just specifies those configurations, which might be infinite, which are a win for player. And a strategy in a game is winning for player. There are two ways of saying this. Sorry. There are two ways of saying this. One is that the strategy is winning if against any counter strategy, it always, when you play maximally, results in a winning condition for player in the game. Or alternatively, and this requires a proof, alternatively, a strategy is winning if any maximal play for player results in maximal play for player results in a winning configuration of A. Okay, we then a strategy from a game A to a game B, i.e. in a game like this, is winning if any maximal play for player, if with respect to any maximal play for player, a win in A implies a win in B. Because of this this fact, winning strategies compose. Really, to underlying this is an assignment of winning conditions to games, which is such that the winning conditions of the dual game I got by taking the complement of the winning conditions of the original game, and the winning conditions of a parallel composition of games is got by taking the disjunction of the winning conditions of or if you like, union of the winning conditions of the two games. So winning strategies compose. We'll be looking at those in the moment. They come up in looking at dialectica categories. There's something else we can do in these games, which is can be done quite directly because of our emphasis on causal dependency. Namely, we can make some events or moves in the game invisible as far as one or other of the players is concerned. And we can do this by having an access level associated with the game. You can think of the access level as being a set of rooms, and in some rooms you can see other rooms, maybe through one-way mirrors and so on, but in other rooms you can't see what's going on in certain other rooms and so on. So you can think of this as this is an access order, and then we can restrict the game so that causal dependency, we can restrict the games and the strategies so that causal dependency respects the access order, and in this way restrict strategies to the access order. It turns out that such lambda strategies, which are with respect to an access order lambda, compose. So armed with this, we can look at Dialectica games, which are like those games which we saw in Recovering Geometry of Interaction. They consist of just a purely player game in parallel with a purely opponent game. But this time with some imperfect information that says that opponent is in room 2 and player is in room 1, and opponent can see players move, but not the other way around. So now, when we look at deterministic strategies between such Dialectica games with this imperfect information, we don't get quite the maps we had before with geometry of interaction, because the forward part cannot, the moves in B1 cannot depend on moves in B2, because it's only the B2 moves that can causally depend on the B1 moves. They can only be, the room 2 can see 1, but not the other way around. So that means that we end up with a restriction on the kinds of maps we have for geometry of interaction. In other words, we get a restriction to these things which are called lenses. And being winning means that we have this situation here, which will be familiar to Valeria, because it's exactly, because what we've done here is essentially recovered her Dialectica interpretation, Dialectica category, but based on Berry's stable functions. So if you were to follow through your construction on Berry's category of DI domains and stable functions, you'd end up with a category which was equivalent to these Dialectica games with deterministic strategies between them. And I suppose many of you know this is important. This is historically important because it gave Gödel a way of understanding how to translate proofs into higher order functions. And it has applications which were first, I think, exploited very significantly by Causal, but have been followed up with tremendous success by Ulrich Kohlenbach at Darmstadt. Valeria will be well aware of the fact that the second half of the thesis was not on Dialectica categories, but on a variant that Jean-Yves Girard suggested. And that variant corresponds to replacing the one-way signaling that we see in Dialectica games by a non-signaling condition. So we just change the access levels to just a discrete order like this. You have the two rooms, 1 and 2, and in neither room can see into the other. In this case, deterministic strategies correspond to pairs of stable functions.
Glynn, your 10 minutes are coming up, okay?
Okay, fine, thanks, yeah. If we look at, while we're there, we can look at, another generalization where we might, to Dialectica games, where we have games which comprise n-fold alternating polarity parallel compositions of this form, where we generalize the access order to be of this form too. And then if we look at strategies between such games, we recover combs that have been invented in quantum architecture as a higher order way of disciplining the quantum circuits and the string diagrams that are used to reason about them. If we look at non-deterministic strategies between Dialectica games, we find they correspond to optics built from stable spans this time. And I'll remind you that an optic can be viewed in this kind of way. The forward part and the backward part coupled together by some residual Q, where, strictly speaking, we can wiggle this Q up and down, so we have really an optic associated with an equivalence associated with that way. We can jiggle Q up and down in this intermediate part here. While strategies between Dialectica games correspond to such optics. We can, we've looked at games which are just parallel compositions of purely player or purely opponent games. What we could do now, what we do now is just keep the imperfect information that we had from Dialectica Games. We say one is below 2, so you can see from room 2 into room 1, but not the other way around. But we don't make any assumption about the nature of A. It's not just simply a parallel composition of two of a player game with an opponent game. Because the game has got to respect the access order, the only causal dependencies in the game which relate different polarities are the ones where opponent awaits player. So the game comprises an initial player part followed by a dependent opponent part. And its configurations correspond to initial player configurations union with dependent, possibly dependent, subsequent opponent configurations. So another way of seeing such a container game is as a dependent sum, where you think of this, you think of the x's as being the shapes and the A2s as giving the positions associated with those shapes. And this time, a deterministic strategy is a bit more complicated. It corresponds to something described, which is called in literature a dependent lens of this kind. So in other words, it can be written as a sigma pi type, or less standardly to an element of an isomorphic type, a pi sigma type like this. And here I'm using constructions of dependent types that exist on event structures and were discovered way back in the 80s when Valery was around in work with Thierry Coquin and Carl Gunther in extending basically some of Girard's work on dependent types, and in particular for system F. All right, so we recover dependent lenses. Here there might be something new. What about those container games with the imperfect information, but no longer assuming that they factor into a parallel composition? What about those container games, but with possibly non-deterministic strategies between them? Well, they correspond to a form of dependent optic, which takes that latter characterization of optics that we saw earlier, and but this time with respect to a dependent product associated with stable spans. The other dependent product we were using was associated with stable functions. This time, this is a slight generalization in which we insist that the non-deterministic output always lies in the right type. And I won't go into there is well, I'm borrowing some notation from I could, because of the closeness between stable spans and profunctors, and the fact that profunctors are like a kind of Kleisli map. I can borrow some of the notation of Eugenio Moggi in order to give a somewhat informal explanation of how you compose these things. But anyhow, in this case, one finds a characterization of strategy, non-deterministic strategies between container games as a kind of dependent optic. This possibly is new, I don't know. Another thing I'd like to stress is that the functional paradigms that arise inherit the enrichments that we've found on strategies. We've enriched strategies with probabilistic and quantum structure, and this we've recently realized that fits inside a general scheme, which harks back to those parameterized categories that I talked about right at the beginning. So all these enrichments to probabilistic and quantum strategies and so on fall within this general scheme.
But now I have to stop, Glynn. We are getting too close to.
Okay, fine. Yes, yes.
If you don't, I mean, I'm sorry to be such a monster.
Okay. But what I can say is, let me just finish this bit. The events and their causal, the limits and polarities help orchestrate the dynamic linkage that goes on in composing the enriched strategies, and I've tried to indicate in this diagram here. Okay, so the functional approach can help tame the wild world of concurrent interaction through simpler models, but those simpler models are being required quite a lot of ingenuity to be discovered. So although there's a cost in developing in terms of technology needed to develop distributed games and strategies, they do provide a broad general context for interaction, which then specializes to functional paradigms, also in providing enrichments to various probabilistic and quantum real number computation. And if you want to read more, it's been rather rushed, I know, then there's a LIX submission, which probably may just always stay like that. Let's see, but it's archived here if you want to see more. But thank you for your attention. I'm sorry for probably going over, did I? Almost.
Thank you.
Okay, thank you.
That's fantastic. That is really a beautiful discussion.
You're always very nice. Thank you.
So I think I'm opening the floor for questions. I mean, I have quite a few, but I don't want to stop from asking.
Thank you. Oh, it's nice to see Andreas. I've not seen Andreas for a few years. Hello, nice to see you. It was in Sweden, wasn't it, last time? In Stockholm. You probably won't. Yes, I mean you meet. you're the very famous person.
Myself and ask a question.
Go ahead.
So this goes back to the very beginning. So the event structures before any polarities, winning conditions, and so forth, just the original event structures.
Mm-hmm.
Suppose I claim to have in my pot event structure. I don't tell you what the structure is, but I tell you what the set of events is, and I tell you what the configurations are. Of course, I could be lying. I could give you some things that I claim are configurations that don't actually come from any event structure. Mm-hmm. Is there a criterion? If I give you what I claim are configurations, is there something that can be checked easily about those configurations to say there exists an event structure leading to these, or perhaps even better, there exists a unique event structure producing these configurations?
Well, I suppose the characterization of these domains that you get.
Sort of intrinsic characterization.
So there would be that really refers, the DI domains I referred to would be the characterization. So they're distributive domains, distributive Scott domains, which satisfy an axiom, inductive axiom, Gerard Berry called it, which is that any finite or isolated element dominates only finitely many elements. That's it. There are other ways, there are other characterizations in terms of complete primes as well, that they form a kind of basis. But I think the more standard mathematical one is that one in terms of distributed domain satisfying that axiom.
Okay, good. Thank you.
I'm not seeing other questions, so maybe I can ask one or two. There's a Peter Hines. Okay, Peter, go ahead.
Wait, Valeria, I think Peter has his hand up.
Nice to see you again.
Good day, how are you? So, question may not make sense, but thanks for the talk anyway. So, at the beginning you mentioned compact closed bicategorizations. Now, when you were talking about the geometry of interaction parts, you were showing the usual pasting of diagrams and summary of paths that you see in both Joel Street and Verity's interstructure and in Smith-Amsker's GOI structure.
Yes.
Now, these both use different conventions. The Joel Street and Verity is the horizontal pasting squares, and Smith-Amsker's mentioned the vertical basis squares. And I was simply wondering whether this gave the bicategorical structure in that particular setting.
I'm not sure if I'd heard you properly, whether I could answer correctly anyhow, but okay. It got very hacked up. Maybe I can just say I glossed over the bicategory, the two cells. So you can look at rigid maps. So you've got two strategies going into a common game, which might, of course, be of the form A parallel B, and you can relate them by, if you relate them by rigid maps in the standard way, they're both going down to the common game, and you have a rigid map. A rigid map means preserves the order. Then that would be that two cell would correspond to the stable ordering on stable functions. And if we also have more general two cells that just think that they're not necessarily rigid, and they would correspond to the Scott ordering on these things. So you're really connecting up the bicategory with order enriched categories. That's right, where the rigidity of the two cell corresponds to stable ordering or that kind of thing, and that would be inherited by the GOI construction. Now, pasting diagrams, I'm not a natural category, so when people say that, I shake a bit, because I do as much category theory as I need, and generally no more, to be honest. But but I've been stretched a bit. But I hope that helps anyhow.
That helps a lot. Thanks very much.
Right. I mean, my competence with the Zoom is not so great, Glynn, so that's why I'm kind of keep going up and down here in the gallery to see if there's more people wanting to ask questions. But meanwhile, can I
ask people questions? Because I know that people have thought about dependent optics and so on, but I don't know much about them. Is what I mean, don't. If it's not new, please say. I mean, the dependent optics was a discovery to me. Is that well known, or is that surprising? Is that the kind of thing that?
Well, I find it surprising myself. I was going to say that if you go back to your slide 16, in 1991, I had when we had the CLICS meeting in Aarhus, I had a picture very much like the one on the bottom. I actually kind of had to look at it recently. The one that has the maps going triangular up, triangular down, triangular up, triangular down. So some of the, but it didn't work then, because that one, Mm-hmm. So in the CLICS in Aarhus, I had this picture, very much was my last picture when I talked about the Girard variant of the category. And the difficult was to make it compose, right? So I kind of, the only way I could, I said I could try to use fixed points, but it wasn't good for me then and there. I did not want to use fixed points because my whole motivation was from the logic, and there was no point at that stage in having kind of fixed points in the base category. So so some of this stuff that is not dependent, it seems, it looks to me like, okay, if I'm clever enough with my event structures and my categories of domains, I can make the compositions work, right? Because that was always the problem with categories of games, right? Andreas kind of know all about it. So, but the dependent thing really seems different, and I don't understand it very well. But if you're thinking about that from the logic point of view, then you're making so many identifications, right? And so my question instead of comment is about this business of doing, I mean, can you go back a little bit more about the picture where you have A parallel to B, parallel to C, and the pullback happening?
Oh, so yes.
A while back, yeah. Okay.
I'm going the wrong way. Sorry for that. Yeah.
That one, yes.
That one, yeah.
Because you know what I'm kind of surprised is I do not know how to think of that more categorically than it's written there. It is a bit funny, isn't it? I mean, it's not a proper pullback, and
well, it is a proper pullback. But what I'm doing is dropping the polarities and I'm forgetting about polarities temporarily to do this. So what I'm doing is I'm taking the sigma and tau. They don't point to the same place. So I have to, first of all, I have to forget about polarities because that's not so that's one thing. But then I need to pad them out. So I pad this out by identity on C. I pad this out by identity on A. Get that thing. Then they are pointing to the same place. And then I can do the pullback. So it really is it's a pullback of total maps of event structures. Right.
Yeah, that's the thing that I hadn't understood very well. And I was kind of trying to remember, what was Robin Milner's dictum about stuff? Was it concurrencies, parallel composition plus hiding or something?
Oh, that's Samson, I think, largely, yes. I think Samson has pushed that. Yes, that's what's happening here. This is a parallel composition, a synchronized parallel composition where you're synchronizing over B. And this is very like a Robin Milner style synchronization over B. And that then gives you stuff, if you like, neutral events, neutral moves where player and opponent where the tau and sigma have played together. So you've got a completed move there, and then you want to then hide it. So that's where this business of composing with this is a partial map of event structure which is undefined on B. The composition is partial, and then you can always there's a factorization property associated with partial maps. There's the factorization system. Namely, you can just go to a kind of a minimal. You can just basically restrict that partial map to its domain of definition, and that gives you the composition of strategies. So the parallel composition is this guy here, and then the hiding is done by this projection to the visible part.
Right. Yeah, now that's very, very exciting, very, very interesting. I like this. I really don't like very much the fact that it's all based on a compact closed category, because I keep complaining to people that for logic this is very, very bad, because
but remember, as soon as you add winning conditions or payoffs, you get star autonomy, and then of course this is a linear model of linear logic. If you want to do intuitionistic logic, you're going to have a bang, and then if you want the bang, then you're actually going to have to work with more complicated games which have got symmetry in them. Because if you, for example, take omega copies of a game, it's not going to be a comonad because the copies get in the way. But if you say that this copy is the same as that one, then you can say up to symmetry. And then you can talk about maps being equal up to symmetry, and then one can make sense of you have a comonad, and then you can start addressing intuitionistic logic.
That's fantastic. But maybe we should thank you again and stop the streaming, because it's
okay. Yes. Thank you very much.
Thank you so much.
Thank you. Thank you.
I'm sorry. Whoever was the IT person saying I've forgotten. I got excited about talking about